The numerous scientific and technological advancements of the 21st century would not be possible without the aid of computers. However, regardless of how many processors you hook together, there are immutable physical and mathematical limits to what classical computers can do. But what if there was another way? Let me introduce you to a little something called quantum computing. Quantum computing makes use of certain fundamental properties in quantum mechanics in order to perform logic operations. Two of the most commonly utilized properties are superposition and entanglement. Let's start with superposition. Take a look at this coin. It has two possible states, right? Heads or tails. If I flip it, you can clearly tell which state the coin is in. Now, let's make things interesting. Until I take off this lid, I have no idea what state the coin is in. Therefore, prior to checking the result, I could say that its state is heads and tails simultaneously. The coin is, in essence, in a superposition of heads and tails. But how does any of this relate to quantum computing? All classical computers work by storing and manipulating data using bits. Each bit can be in one of two states, 0 or 1. By adding more bits, the amount of information that a computer can process grows linearly. A quantum computer, on the other hand, does things a bit differently. A quantum bit, or qubit, can be 0, 1, or a superposition of 0 and 1. Just like the coin, as long as the state of the qubit isn't measured, it can be in both states simultaneously. Only when measured does the qubit collapse into a single state. As you add more qubits to a system, the amount of information it can process increases exponentially. This means that a quantum computer with only 50 qubits could already process over a quadrillion values. The other commonly used quantum property is entanglement. When a pair of qubits becomes entangled, the state of one will indicate the state of the other 100% of the time. This connection is instantaneous and works over any distance. As soon as the state of one qubit is measured, the state of the other is known without looking. So, what does it actually take to build a quantum computer? Well, due to how sensitive quantum processes are, quantum computing operations generally need to be carried out at around 10 millikelvin. That's almost as cold as my shower in the morning. In order to achieve such low temperatures, modern-day quantum computers require massive cooling systems. The qubits themselves, however, only take up a tiny chip which sits at the bottom of the system. Hopefully one day, quantum computers will be far easier to construct. Once that time comes, they will be used to run previously uncomputable algorithms, revolutionize cryptography, and simulate the natural world in unprecedented detail. Quantum computers have the potential to bring about a new era of limitless computational possibility.